record this. Okay, so C8HHO. Saturated is C8H18. So again, we're missing 10, which means we have another 5 degrees of unsaturation. Last Thursday I gave you alkenes. This time I'm giving you benzene rings. So that's probably evidence that we have a benzene ring again. So again, we want to look in the IR and we want to see if it's consistent with there being a benzene ring. And I see the peak at around 1600. It's smaller than it was in the previous one. And I see the peak at around 1500. Right, so there's the ring breathing, that's present again. I see a lot of stuff above 3000 here. And so there's the sp2ch stretching. And then I want to look at the other ones at about 760. That's consistent with either a monosubstituted or a meta-substituted benzene ring. And then I'm going to combine that with the fact that I have 5 hydrogens here in a relatively nondescript peak at around 7.2. So the combination of these two peaks at 710 and 740, 760 in the IR and 5 hydrogen integration, that tells me I've got a monosubstituted benzene. So I can draw that piece, right? 710, 760 in IR, and 5H integration around delta 7.2. The other thing I can look at in the IR is there's this sawtooth pattern here. This sawtooth pattern right here in that region between 1800 and 2000 where really nothing else shows up. That's present in a monosubstituted benzene that would not be present in a meta-substituted benzene. So you'd still have these two peaks in this kind of 700 and 760 range for the meta-substituted, but you wouldn't have that sawtooth pattern. And you see that that sawtooth pattern wasn't there in the other spectrum. So now I want to look and see what else I can tell. Here, down here in the carbon NMR, right, we've got 4 peaks, 2 fairly tall peaks, one that's shorter, and then one that's really short down here close to 140. This one close to 140, that's the carbon that's quaternary. There's no hydrogens on that one. That's the point of attachment of the benzene ring to other things. This is the CH, that's just one carbon hydrogen, right? There's a single carbon opposite that. And then these tall peaks are the symmetrical pieces of the benzene ring, right? So the 2 taller peaks will be these carbons, the ones where there are 2 identical carbons, and then this one is the short peak because it's quat, and then that one is the shorter. That's just because there's 1 carbon there. So everything's consistent with a monosubstituted benzene, and that actually uses C6H5. So there's not a lot left. There's just C2H3O remaining. I got to figure out what that is. The carbon NMR is actually very useful in this case. Because we have 2 peaks here that are in the region down around 50. So both of these carbons are in that region where you're close to electronegative elements. And what that tells me is that I have 2 carbons attached to oxygen. So both of these 2 carbons, this remaining C2H3O, in the 13C NMR, we have delta around 50 ppm for both of those. Both of those carbons are attached to oxygen. There's only 1 oxygen, so those 2 carbons must be attached to the same oxygen. So I've got an ether. I need 1 more degree of unsaturation as well. The only way to get that degree of unsaturation is to make a 3-membered ring. So we're looking at an epoxide where the benzene ring is attached And we would expect to see an ABX pattern here for those three hydrogens, where these geminal splitting is a fairly large coupling constant. And then we've got smaller ones for the trans and the cis coupling. And if we look in the NMR, that is indeed what we see, right? We see an ABX pattern where there's one hydrogen that's further downfield, right? That's the one that's attached to both the benzene ring and the epoxide. And then we've got these two hydrogens that are upfield, right? That are what looks like doublet of doublets, right? Because they're splitting each other, and they're also split by the hydrogen that's across the ring, right? And they're all in that region, right? We've got like 2.9, 2.8 and 3 and 4. They're all kind of in that region that you would expect for hydrogens that are attached to carbon that's adjacent to electronegative element. We should be able to see in the IR peaks that are consistent with a carbon-oxygen stretch, and you're seeing them. They're slightly different frequency from where you would expect to see a carbon-oxygen stretch, right? We're seeing this at around 900 and this one at 1,000. We're used to looking for carbon-oxygen stretches more in this kind of region between 1,000 and 1,200. The reason for that is the three-membered ring would we expect that CO stretching to take less energy than a normal ether. And we're seeing two peaks. We've got two different kinds of carbon-oxygen bonds, so it's not surprising that we're seeing two different peaks. And those stretches that are about 9, right? This one's at about 890 to 900. This one's about 990, something like that. You'll also notice that 910 and 990, those kind of two peaks, is often where we see the vinyl group. Right, the vinyl group often has resonances at 910 and 990. So it's also possible that these are the bending modes for the vinyl group. They're a little broad. The vinyl group bending modes are not usually that broad, which is why I think they're probably carbon-oxygen stretches rather than the vinyl.